most of your schoolings. So if you've not really understood that, then we'll try to understand it right now. Then now the reason that I'm emphasizing on probability is because probability has a lot of applications in the real world as well as in computer science, right? So if we look very carefully at probability, yes, so if we look very carefully at probability, we will find many such applications of probability in real life. Like, for example, if I go outside and I meet up with a friend who is not corona positive, what is the probability of me catching corona? So, all of the projections that are being made currently regarding this particular disease are being made on the basis of probability. There is a sample set, there are events, and these events and sample sets are related to each other, and there are calculations being made based upon the basic laws of probability, right? So in this particular course, what we're going to see is what is probability first of all. Next, we're going to actually identify what are the various rules that are a part of probability and how these rules modify themselves or change themselves based upon the situation. So the two situations that we are concerned with here are dependent and independent situations. So let us just very quickly get started with this particular session. Now, here again, before starting the session, I'm giving a disclaimer. Whatever we are doing in this session, questions related to this particular session will actually be explained between the session. So, after each and every section that I complete within here, there will be a short time where I'll be scrolling through the whole chat here, and I will actually be answering your questions. So if you have any queries throughout the whole session, please make sure to write them in the chat. Also, for queries that are not related to this particular course, I would recommend that you put them down any which ways so that they can be answered in a later course. Right? So please bear this in mind. Please keep interacting so that this is an interactive session rather than just, a one-way session here. Um, Another thing that I would like to make very clear is the fact that this particular course is going to be, or this particular session is going to be theoretical. So if you're looking for an implementation in, say, for example, R or VECA of all of these probability concepts, then that is not going to happen in this particular session. We will obviously be taking it up in some subsequent live sessions. All right, so let's quickly get started. First, we are going to look at what probability is and what are the practical applications of probability. So we'll be looking at the computer science based applications also, and we will be looking at the real life applications of probability. Next, we'll be looking into what are the basic probability ideas that we need to know about, and we'll be looking at some sums for the same. There are also two rules that we'll be looking at here, the addition rule and the multiplication rule. Next, we'll be looking at, as I've already stated, we'll be looking at the dependent and the independent entities. So that is what we're going to do here. We're going to look at conditional probability from the point of view of two events which are dependent upon each other or are interacting with each other, and we are going to look at probability from the point of view of events which are not interacting with each other or are independent of each other, right? So before we go forward, let me just quickly scroll through and just greet all of our attendees today. Hello Ajit Sahu, hello MK, hi Song and Song. All right. The rest of you can also please put up a hi, a good evening, so that I know how many of you are here and I can just call out your names and then greet you all so that this becomes a bit more interactive in nature, right? So please go ahead and at least put up a greeting here so that there is some interaction of some kind. Again, please put up your queries as and when you get them. Right, so let's quickly get started with our first topic, which is actually an introduction to what probability is. So what is probability? Now ideally, if you look at the term probability, it means possibility, right? It can be synonymous with possibility. So probability is actually the possibility or the likelihood of any of the events that we're talking about actually occurring in real life. So for example, what is the probability of the sun rising tomorrow morning? There would be some probability, there would be some possibility based upon what you've observed in a certain set of days or in a certain set of months. For example, you can say with some surety that maybe the sun is going to rise tomorrow, or the sun is not going to rise tomorrow, or whatever other probability or possibility might be there, right? Another thing we need to remember about probability is that probability is actually concerned with random events. So two random events which may or may not be related to each other, or say for example, even for that matter, three or more random events which may or may not be related to each other are actually occurring here. And why is the reason that we're considering them for a probability? Because they actually belong in the exact same environment, right? So as I draw this, you will actually see that there are some components of set that comes up here, there are some components of logic that come up here, and that is because probability is actually that you taking up an event and trying to find out how that event is created. So we might get them in the form of, say, Venn diagrams for that example, so that would become the events, and how are these various events interacting with each other. So that is what probability is. After the interaction, what is the likelihood of that particular event actually occurring? Now probability is always going to be between 0 and 1. So any of you who are trying to do a sum or trying to solve a problem with probability and are getting probability of the type 0.25, please note this is not a possible probability. Now the reason for this is, we'll be seeing later on. It's because each and every value in probability is always a proper fraction, right? Reason for that we'll see in just a few minutes, but please remember that whenever you're taking probability, it will always be in the form of proper fraction, and proper fractions are such that their values are always going to be less than 1 or max to max equal to 1, right? So the value of probability will always be between 0 to 1 if you get a negative probability, or for that matter, if you're getting a probability that is greater than 1, there is some fault with the calculation or the understanding of the questions somewhere, right? Next, let us look at sample space. Sample space is the actual set of events or the actual set of occurrences where everything is happening, right? So whatever becomes a part of your environment, whatever entities are a part of your environment, whatever events are a part of your environment will become your sample space. And events are actual specific actions that are under consideration, right? So if there are very specific actions under consideration, say for example, I am picking out an apple, so that is specific, right? I'm going to a vendor picking out an apple, I'm not selecting any other fruit, whereas I've got an option for selecting various fruits. So all of those options presented to me are the sample set, and me picking out an apple is the actual event. This is how sample space and event are actually linked to one another. We'll be looking at further examples of these later on throughout this session. Next, let us look at some of the real life as well as computer science based applications of probability. So wherever we've got planning, all right, any kind of planning, any kind of strategizing, any manner in which you need to estimate before a certain event occurs, whether it will occur or not, how it will occur, what is the probability of it occurring, what is the possible effect of an event occurring, in all such cases you will apply probability. So within weather planning, what do we do with weather planning? We take some variables, say x is humidity, say for example y is let's take, apart from humidity, we could have frigidity, we could take z, which is the amount of precipitate that is already precipitated in the past few days, so the amount of rainfall that was there in the past few days. Taking all of these variables, putting them together in a certain scenario, and then estimating the possibility that it might rain tomorrow also. That is what weather planning is, right? You taking up a certain set of weather based variables, analyzing them in a given environment, and then predicting whether or not this would happen, or it would be sunny tomorrow, or it would be windy tomorrow, or it would be stormy tomorrow, right? Next, sports strategies, or for that matter even in games, right, or in politics, you need to look at your opponent's strategies. In all of these three places, looking at the opponent's strategies, analyzing the most played game of theirs, or analyzing the most played motto or agenda of theirs, and then formulating your plan or your manifesto or your agenda based upon factors which will counter those agendas. So how do you do that? First, analyze their agendas, analyze their salient points, take those as variables, find out the probability that they're going to use that, then take up your agenda, find out what is the most commonly seen or what is the most effective or which is the most probable to actually break down the opponent's agenda, right? Next, in insurance, if you ever see an insurance company's legal papers or documentation, you will actually understand that they strike off the most probable causes, right? So for example, if there is an act of god, let's just take a you know say for example a shop insurance for that matter. I've got a business, I've got a shop, and I've taken out an insurance on that particular shop. So if there is an act of god, say for example, or there is a self vandalism, right? What is self vandalism? Self vandalism is when I myself am setting fire to or breaking down or somehow damaging my business in order to ensure that I get the insurance payoff, right? So what do these insurance agents or insurance companies do? They strike out both of these cases of coverage. So if it is an act of god, we're not going to cover it. If it is self vandalism, we're not going to cover it. Why is that? Because in these particular cases there is nothing that the insurance company would do, because in most cases, depending upon where you are currently, sometimes you would see that act of god has the largest probability of happening. Like for example, if you are in a flood prone area or if you are in an earthquake prone area, every second day you would have an earthquake, or every month you would have an earthquake. How many times you as an insurance company would be giving the payoff? So a probability analysis is done of the act of god, and then an estimate is made on whether or not to pay out in case of an act of god. Next is self vandalism. Again, a similar analysis is done on how many people actually self vandalize their businesses, and if the probability is high, then they put out a clause that this is also something the insurance is not going to cover, right? So these are some of the real life examples. Let us look at some of the computer science based examples. So many of you have already seen this SEO. Some of you might be typing down and searching for what SEO actually is. I'll just quickly no dear, no dear. Chandrabha Chatterjee, no, this course is not enough for data science. This course is not at all completely for data science, right? So this will form the basis of data science in many cases, but it is not the complete end all and be all for data science. This is just a part of it. All right. Uh, Hello Ajay Goel. Hi Ujwal. Hi Bodhisatta. Hi Asif Khan. Hello Raj. Mr. and Mrs. Singh. Hello. Okay. Yes, so we'll quickly continue with this. So, first of all things, let us look at the applications of probability. We've got SEO, which is search engine optimization, you finding out the pertinent keywords, probability of a person actually searching for that keyword, and then putting the keyword as a part of your web page or a part of your video or a part of all of your data which is available online. So that is what search engine optimization is. So first step is finding out the probability of a person using the keyword that you're putting up as a part of your particular web source, right? Next comes natural language processing and machine learning and data acquisition and machine learning. So what is natural language processing? Natural language processing and machine learning go hand in hand many a times, because 90% of the time you are teaching a machine to understand natural language, right? Humans understand natural language is much easier. You need to code natural language processing within a machine. So in machine learning, we often see a component of natural language processing, and we see that probability plays a large role here, because a machine will first learn all of the syllables of any language that it most commonly encounters. So for example, the vowels of any languages are first acquired by a machine while learning NLP, because the vowels are what actually um, makes the language, right? It makes the syllables. So a, e, u, these are the vowels that make any syllable in any language, and that is what is first acquired by any machine, because it finds out that the probability of pronouncing or understanding or analyzing these parts of the alphabet is actually much larger than any of the consonants. So for example, if you take it in English, a, e, I, o, u will first be acquired. Z, u, X. These are all of the lesser used alphabet in our English alphabet. These are some of the lesser used letters. So these might be acquired later on, or these sounds might be acquired later on. What do we get as intermediate? As intermediate, we get all of those confusing sounds like C and S, wherein can be used for both. The sound can be used for both C and S, or for that matter, confusing sounds like T and D, where T and D don't really make that much of a difference. So these come within the intermediate pattern, right? So that is how probability will see which letter, or probability will help the machine in understanding which letter or which vowel or which sound or which syllable comes up to it in the most probable manner, or in the most frequent manner, and then accordingly it is going to acquire that language. If you're trying to analyze traffic, or if you're trying to analyze an algorithm, again you would require probability, because you need to analyze exactly which path to take in order to achieve a goal in both of these cases, right? So if it is an algorithm, which part of the algorithm's fork has to be taken in order to solve a particular problem, or for that matter, if you've got congestion in a system, so before you ever put up any packets across in the system, you can have a probability analysis of which parts of your network have a possibility or a likelihood of congestion occurring. So there are various actual congestion control mechanisms which also help you find out the relative probabilities of congestion occurring in any particular part of your network based upon some features there, right? So that is a completely different topic. Anyways, that is where we find out the probability of congestion occurring. And if this particular probability materializes, or if the event materializes, based upon the probability of the event materializing, we can have, or we can plan contingencies for such congestions, so that the transfer of packet from sender to receiver is still maintained, right? Lastly, we've got cryptography. In cryptography, probability is very, very commonly used. Just one example will help you understand that. If you are converting any plain text into ciphertext, how do you ensure that the ciphertext is not going to be cracked by any kind of hacker? Very simple. You shift, turn, manipulate your plain text using such an algorithm which has the lowest probability. I'm not saying no probability, but the lowest probability of getting cracked. So the more twists and turns you have, like for example, you've got AES, DES, you've got various encryption algorithms, right? RSA for that matter. So using all of those encryption algorithms, how do you decide which one is the best for you? So for your system, whichever has the lowest probability of getting cracked by a hacker will be selected as your particular cipher or cryptography technique. So that is how probability in the most common ways and in the most computer science ways would help you as an application, right? Next, let us look into basic probability. Before we go on to basic probability, let me just quickly go through the chat here. Okay, so there are, can we learn maths for machine learning? Where can we learn maths for machine learning? I guess on this particular channel only, Mohammed Shahid, right? So we've got, yes, Chetan, search engine optimization. Yes. So in machine learning, if you see further ahead as you go through machine learning, probability is also very important within machine learning. There are other maths like, for example, logics, propositional logics, proportional logics, etc., which you could study further on. So please stay tuned. Within this channel, you'll be finding many such videos and live sessions which will actually carry through here. Okay, yes. Hitul Kannan, what is an event? So I will quickly just go through what is an event. Event is an action, and you will see later on examples of various events. So let us just quickly go on to basics of probability. So the first thing that we're going to look into probability is what is the formula for probability, right? Why do we require a formula for probability? Because if we do not know how to find out the probability of the tiniest thing, how do we extrapolate that idea to large things? So first of all things, if you're looking at probability of any event, say for that matter, our event is A. All right. Now, event, I will again iterate this. An event is any action that is occurring in an environment, right? So if we have an event A occurring, or if we have an event A which is under scrutiny, some action that we're trying to scrutinize, and if we want to find out the probability of that event occurring, then we've got two things to take care of. One, that we have a sample set here, which is also considered as the total number of occurrences, and two, that we have the number of times that the event has occurred within that sample set. So imagine this, for example. Say um, you have a possibility of eating an apple as a fruit 3 times a day out of a week, right? So 3 times a day out of a week, you have a probability that you would be eating an apple. If this observation has been done, say, in the third week of January, then I would like to know the probability of you selecting an apple to eat in the morning in the fourth week of January. So, what do? We actually analyze this whole idea. So, we've got our third week of January data stating that we've got 3 days a week wherein this person is having an apple a day, right? So, we can say that 3 days out of 7, we've seen apple being selected as the fruit of the day. What about the rest of the days? Maybe you are selecting an orange for the rest of the days, right? So 4 out of the 7 days that we had, we would maybe be selecting an orange or maybe some other fruit. So this is how probability actually works. It takes up the actual incident or the actual event occurrences and divides it with the total number of occurrences, whether they are a part of the event or not a part of the event. If they exist in the environment, then they are known as occurrences. All right, so we've actually got number of times the event has occurred divided by the actual number of elements or the number of occurrences of any event within the sample space. Have all of you understood this basic concept? Please make a note of this. This is very, very important because later on everything is based upon this particular probability formula, right? Next, we've got sure event and impossible event. So with these terms, you might already have understood what is a sure event and what is an impossible event. A sure event is something that will happen 100% of the time, whereas an impossible event is something that will never ever happen, right? So let's take an example of both of these. We've got an example here. Picking an apple from a bowl containing 10 oranges. Imagine you have a bowl and it has 10 oranges within it. What is the probability that you will be able to pick an apple? You've got 10 elements inside this, right? So 10 elements implies that our sample set is 10. How many apples were inside this bowl? Yes, can I have a quick answer for that? Yes, how many apples were inside this bowl? Actually, the number of apples was 0. So that means we're getting a probability of 0. Why is that? Because there is no way you can pick an apple from a bowl full of oranges, right? So such events are known as impossible events, right? Wherein you know for a fact that there is no way you can get this particular event with this particular sample set. Let us take an example of a sure event. If you've got a coin which has two sides to it and both sides are head, right? What is the probability of getting a head? So please note, this is a biased coin. Both sides of the coin are head. What is the probability of getting a head? There were two sides. In both sides I can get head. So the probability of getting a head is 1, a complete 1, because it does not matter which side the coin flips onto, on both sides we are going to get head. So it is a 100% possibility or a sure event that we would get head if we are flipping this particular coin. So this is the difference between sure and impossible events, right? Next, let us look at some of the other examples also. These are some of the examples that I've seen in chats all around that many people have a doubt with, and we'll be seeing more such examples as we go through the course. So the second example that I want to look at here is selecting a black king in a deck. Please note, whenever you've got deck, we're actually looking at 52 cards, right? 52 cards are what we are looking at here. We are not looking at the two jokers because they don't really belong to any deck. So what is the possibility of getting a black king? Now please note that there are two black kings in any deck of cards. For this I would actually say that, you need to look at the deck of cards to better understand this. So we've got, I'm so sorry about that. So we've got one king which is actually a king of clubs, and we've got one king which is actually a king of spades, right? Apart from these, we've got two other kings, but they are of red cards, namely hearts and diamonds. So out of 52, the possibility of selecting a black king is one would be a king of clubs or it would be a king of spades. So we've got a total possibility of two, right? So if we take this event as E, then probability of getting this event or probability of this particular event occurring is equal to 2 upon 52, and if you divide this further, you would get 1 upon 26. So this is the probability of getting a black king from a fair deck of cards. Right? Next, what is the probability of getting a tail on a coin? Now, let us consider that on this particular coin, this is a fair coin. So that means one side is head and one side is tail. So there are two possible outputs, right? And from that, the probability of getting tail is 1. So if we consider this particular event as f, then probability of f is going to be 1 upon 2 if we toss a fair coin. Next, lastly, what is the probability of getting 6 on a fair dice? So if we have a non-weighted fair dice, then we could either get 1 or 2 or 3 or 4 or 5 or 6. So we've actually got 6 possible outputs, right? From these 6 possible outputs, how many times are we getting 6? We're getting 6 only one time. So if we consider this event as G, then probability of G occurring is actually equal to 1 upon 6. So these are how we can actually find out the various probabilities of individual events that are occurring in any particular system. Anyone having any questions here? Yes, that's lovely. That's actually very great. Yes, please excuse my constant throat clearing. It's because I've got a slight scratchy throat currently. Yes, good, good, wonderful. Next, let us look at the two most important rules that are a part of probability. 90% of us would just look at these rules and get scared. Don't. It's extremely very easy. Think about this in the most logical manner possible. First, this is already a part of set. Whatever was initially a part of set theory has now been modified to fit probability. That is it. So if you're clear with set theory, you will find that apart from the P given here, everything else is actually a part of the set theory, right? That is because even probability works on the condition that everything is going to behave as if it were a set of multiple events, right? So let us see how this actually works. If we've got two events, or if we've got three events, or for that matter, if we've got four or five events, in any of these cases, we can actually apply this particular addition rule. In order to do that, we first need to understand how the addition rule is working, right? For the purpose of this, what I'm going to do is I'm going to simply draw a Venn diagram, and we're going to have two events such that we've got event A and B, and they are interacting with each other, right? So when they're interacting with each other, what is A union B? If we think very carefully about it, A union B would be this whole part, whatever is a part of A and whatever is a part of B. But think about it. We selected whatever is a part of A and we covered this area here, right? And next, while trying to cover up all of the parts of B, we again covered this particular area, which is a part of the intersection. So this area is getting covered twice. Do we need it twice? No. So what do? Subtract the intersection from there. So that is exactly what is given in our particular formula. We've taken all of the parts of A, we've taken all of the parts of B, and because A intersection B, which is the common area between A and B, is coming twice, we have deleted it once. So therefore we are taking only whatever is coming one at a time. We are not taking in repetitions. So if we've got probability of A union B, then probability of A union B is actually equal to probability of A plus probability of B minus probability of A intersection B. This logic, if it's clear to you, you can easily understand what is the addition rule for three events. Let us look at that too with a Venn diagram. So suppose we've got an environment such that we've got A, B, and C interacting with each other, right? So ideally, what do we do when we want to find out A union B union C or probability of A union B union C? We just simply shade up all of the required area. Now, as you can see, all of the intersections between the set will all get mapped out twice. So A intersection C will get mapped out twice, A intersection B will get mapped out twice, and I'm so sorry, B intersection C would also get mapped out twice, right? So what do? We very simply just subtract all of these intersections once. So we are considering them only once, right? This is what we're doing here. But look at this tiny, tiny portion in between here, which I'm going to mark in green. This portion got completely deleted out, right? Why did it get deleted out? Because we subtracted these elements, and this green portion is actually coming as the intersection of all of these three elements. So what do? We actually add back that particular element at the end. So this means that we are subtracting the red space. The area that has been shaded red has been completely subtracted, and the area that has been shaded in green has then been added on because it was initially removed completely on the subtraction. So using this logic, we have extrapolated it onto our probability formula, and now we're saying that the probability of three events occurring is sum of probability of first, second, and third minus probability of intersections of all of them plus probability of intersections of all of the three sets, right? So this is how we actually apply the addition rule. Now using this Venn diagram concept, if you have to, you can also find out what is the probability formula for the addition of, say, 5 events, 6 events, 7 events, or n events, because I'm sorry, now you've exactly understood how this is working, right? So let us just quickly look at this with an example. If we've got an event, say for example, P A union B, and that is equal to say 15 upon 20, let us have another event P of A such that its probability is 3 upon 10. Let us have an event B such that its probability is not known, and we've got a complete event A intersection B such that its probability is 4 upon 10. We need to find out the probability of B, and we've been given the probabilities of A union B and A intersection B. It's very simple. Substitute it in this formula and find out what the probability is. So you would get probability of B as 15 upon 20 minus 3 upon 10 plus 4 upon 10. A simple mathematical calculation would then give you something along these lines, which would be equal to 17 upon 20, I guess, right? So this is how much the probability of P of B would be. Let me just have a quick look at this calculation just to check whether or not everything is in order here. Yes, everything looks like it is in order, and this becomes our final probability. So this is how we are actually supposed to consider the events here within addition rule. Another thing that you need to realize here is that the addition rule is an or rule. What does that mean? What is the meaning of an or rule? What or rule means is that we are going to have event A, or we are going to consider event B. We are actually trying to find out the possibility of event A or event B occurring, right? Please note this word or, it's very important. Wherever you have or, it eventually translates to getting a union here, right? So please be very, very careful, especially when it comes to statement problems. Whenever there is a mention of or, they actually mean that there is a union or the addition rule that needs to be applied there. Next, let's go on to the next topic, which is the multiplication rule. Now, multiplication rule on the offset, let us understand that the multiplication rule is an and rule. This means that if two events are interacting with each other, then we are concerned with both A and B, right? Another thing that we need to realize here is that in the multiplication rule, we are 90% of the time concerned with A and B occurring. As a result, either A will occur after B has occurred, or B will occur after A has occurred. We will look at this particular concept more when we come on to dependent or conditional probability. For now, just understand that that is what the notation says. A pipe B actually means A when B has already occurred. And if you write B pipe A, it means probability of B occurring when A has already occurred. So, what is the probability? Now, again, this is a very logical probability. If you look at the formula given here, probability of A and B occurring is actually equal to probability of A occurring after B into probability of B. So B has already occurred, and when B was occurring, there was no A. After B has occurred, what would then the probability be? That would be probability of A after B has already occurred. Now, what is the reason for doing this? It is because the two events here are actually related to one another. They can't really be seen as completely different events, and that is why this is happening. So we're taking the event P of B as it is because at that time, at that certain given time, A was not in the picture. But when A came up, B had already occurred, and that is why we are taking probability of A when B has already occurred. Now, if this has to be extrapolated to three events, say for example, A intersection B intersection C, then what do? We use the same logic, right? How do we use the same logic? Say for example, we actually started off with A. So probability of A occurring, there are no other events here, please make a note of this. So probability of A occurring into probability of B when A has already occurred into probability of C when A and B have already occurred. So if you increase the number of events here, the number of values that come up after this equal to sign also increase. So let us take an example, probability of A intersection B intersection C intersection D, and let's find out what the probability here would be. So probability of A would be the first term because there are no other events currently, into probability of B when A has already occurred, into probability of C when A and B have already occurred, and probability of D when A and B and C have already occurred. So this is how we can actually apply the multiplication rule to find out how two events which are occurring in combination with each other are actually probabilizing in any particular given scenario, right? Next, let us look at an example here. What is the probability of wearing of a person wearing a pant and a t-shirt if the probability of wearing a t-shirt is given as 22 upon 25 and the probability of wearing pants after they're already wearing t-shirt is 3 upon 12? So we simply substitute in the formula. So what do we get here? We get 3 upon 12 into 22 upon 25. So we can cancel all of the values out here. I'm sorry about that noise. We can cancel out all of the values here, and what do we get? We get 11 upon 50 as the probability. Now most of you would have realized that by now that all of these values that we are getting as the final probability have a lower numerator than the denominator. This is because, as I've already stated at the starting, we've got okay, okay, okay. Just a minute there. Just a minute there. So, As we've already stated at the start, we've seen that this particular event is in such a manner that you'll always have a proper fraction here. That is because you've got a certain sample set and the events will be selected from the sample set, right? So the number of events can never be higher than the elements within the sample set. If you've got 10 oranges in a basket, you can pick out 10 oranges from it, but you can't pick out 11 oranges, right? So that is why I constantly keep saying that the values of probability are always going to be between 0 to 1, because every time you find out the probability of any event occurring, it would be as a proper fraction. Okay, tell in Hindi. Fine. So what I'll do is I'll have a combination of Hindi and English. That is ideally because I'm not used to taking sessions in Hindi, right? So what do we do? What do we do? For those of you who require me to talk in Hindi only, I would recommend that you put up your questions in Hindi. Right? So when I answer you all, I would actually be stating all of the answers in Hindi. So for example, if you've not understood something, please put that up, ma'am. ये मुझे नहीं समझ में आया, and write the concept name there, and then we could go through it during the summary. All right. So let's continue on with the session and let's go on to an important topic here, which is sums. Now, these are very, very, very important, right? Now, why are sums important? In order to actually cement our concepts here. So, I mean, I've seen many people making a mistake here. Ideally, I would say before understanding this concept properly, even I would make a mistake here. The first thing we need to find out is analyze the question. What is given in the question? What is asked in the question? These are the two most important things: what is given and what is asked. So, what is given in the question? When we read the question, we find out that there is a coin that is flipped three times, right? So, a coin is getting flipped three times. Now, we are assuming that the coin here is a fair coin, and we are assuming that that fair coin is getting flipped thrice. What are they asking for? They're asking about the probability of getting heads exactly two times. Now, how do we know it is exactly two times? Because they've not given us the word exactly, but they've not given us at most or at least either. Right? So that means we are supposed to find out the probability of getting heads twice if a coin is flipped three times. Now, how do you understand how to find the sample set? This is the first major hurdle that many of us have. How to find out the sample set actually here? Sample set is very, very important because it actually tells you what your base set is out of. Your denominator comes from the sample set. So if it is a coin, this is a very easy thing to remember. If it is a coin, you've got two sides to the coin, right? And how many times is it flipped? It is flipped three times. Carry out this calculation, 2 raised to 3, and you'll find out that you get 8. So your sample set is going to be of 8 outcomes. We'll see what the outcomes are later on, but this is one of the easiest ways in which to find out how many outputs would be there as a part of sample set. We'll see this again with the dice, but for now I'm just telling you how to do that with a coin. So what you do is you take the output for one particular toss, right? So you take the number of outputs that would be there for one particular toss. So if you have a coin, there are two outputs, and then you raise it to the number of coins or the number of tosses based upon your question. It will work for both. If you're flipping one coin three times, it would still work. If you're flipping three coins, it would still work, right? So just the number of, that is what we require here. So if you are flipping a coin two times, possible outputs are 2 raised to 2. Total number of outputs would be 4. So your sample set would be 4. Here we are flipping the coin three times, so the sample set is going to be 8. Take 8 lines. All right, just consider 8 lines given and split all of the 8 lines by 2. Write heads and tails in equal numbers. Split the heads line in 2. Write head and tail. Head and tail after splitting the tails line in 2. Next, split them further and alternate head and tail. These are all your sample sets. This is it. If you've got 3 coins, this is how you do it. If you've got 2 coins, then it's even simpler. You take 4 and you split it up into 2 and 2, where you've got head, head, tail, tail, and then you alternate head, tail, and head, tail. You don't even need to search for all of the various possible combinations here. It is as easy as that, right? So what do we do here? We've actually found out what the sample set is. Now what do we have to do? We need to find out how many elements here actually have heads, right? Heads 2 times, so only 2 times. So we've got a first event here, which is head, head, tail. We've got 2 heads. We've got our second event here, which is head, tail, head, again 2 heads. We've got our third event here, tail, head, head, again 2 heads, and there are no more heads after this, right? That is because, or rather I should say, there are no more events having exactly 2 heads after this. So for our event, we can say that we actually have 3 events that are occurring as per what we require out of the sample set of 8. So the probability of getting, I'll repeat this, please just give me a minute. Yeah, so the probability of getting 2 heads, or the probability of getting head 2 times if a coin is flipped thrice, is actually 3 upon 8. It is as simple as that. So now if you need to extrapolate this to any other situation, this particular concept will remain the same. What happens if you're asked at least 2 times? Then you check for all of those which might have 2 or 3 heads. What happens if you're asked for at most 2 times? It means they're asking for all of those events that have 0 or 1 or 2 coins. So these words are very important here, and based upon those words, the events elements will keep changing, right? Yes, Chetan, very good. It's actually very, very good. Brilliant. Okay, next, let us look at the next question here. So we've got a class of 25 students. Let me just quickly change the color here so that it's more visible. And 10 of them are boys, 15 of them are girls. On a PT test, we found out that 3 boys and 6 girls made it to the top percentile. We are supposed to choose a class representative. What is the probability of choosing a boy or a top percentile student? So be very careful here. They've given you a statement which is asking you what is the probability of choosing a boy or a top percentile student. So from this or, we can understand this is actually the addition rule. Remember I told you that the addition rule is an or rule. It means that whenever you are asked to apply the addition rule, they will give you this word or, right? So choosing a boy or a top percentile student. Now we know that we can select any kind of event. So let us say B is an event where we're selecting a boy and T is an event where we're selecting the top percentile student. Now what is the probability of selecting a boy? Probability of selecting a boy is number of boys that are there as a part of the class divided by total number of students. So we've got 10 boys in the class divided by total number of students, which is 25. Next, what is the probability of actually selecting a top percentile student? So if you look here, top percentile students actually consist of 3 boys and 6 girls. So out of 25, we had 3 boys and 6 girls, all of whom came in the top percentile. So the probability of picking a top percentile student would be 9 upon 25. Next, we need one more element here. Probability of picking a boy who is also a top percentile student. So how many boys are top percentile student here? So actually the question very clearly state that there are 3 boys who are top percentile students here, right? So this is a complete set of all of the elements that we have. We have probability of boys, probability of getting top percentile students, and probability of getting top percentile students who are also boys. Then we can find out the probability of selecting a boy or selecting a top percentile student as probability of selecting a boy plus probability of selecting a top percentile student minus probability of selecting a boy who is also a top percentile student. This would give us 10 upon 25 plus 9 upon 25 minus 3 upon 25, which is ideally equal to 16 upon 25. Again, this is a proper fraction. So this is the probability in answer to the question given here. Lastly, let us look at the last sum given here, which is, yes, if two dice are rolled together, find the probability of getting 10 as a sum. This is the last question that we will actually be doing here. The reason for that is because we are running out of time. I will very quickly go through the conditional probability and the non-conditional or the independent probability. We'll see if we have time for doing the sums here. So if we are rolling two dices, remember our formula: number of outcomes raised to the number of times that it is rolled. So what are the number of outcomes? Right, what are the number of outcomes for a dice? Number of outcomes for a dice are 6. And how many dice or how many times have the die been rolled? Twice. So the total number of outcomes would be 36. So we already have that our sample space has 36 elements within it. Now it becomes very difficult to write down all the 36 elements, because we would have one with 1, one with 2, one with 3, so on and so forth, till we don't get to 6 with 1, 6 with 2, 6 with 3, and etc. till 6 with 6. Right? So it's a very large sample set to write down here. So what we are going to consider here is just that there are 36 elements as a part of our sample set. Next, how many of these are going to give us a sum of 10? Right? So if we require a sum of 10, we will actually have to consider pairs of the type 4, 6 and 6, 4. Now why are we considering this? Because we are considering the first column as the first die and the second column as the second die. Right? So we've got 4, 6 and 6, 4, wherein 4 would be a part of the first die and 6 would be a part of the second die. We're getting 6, 4 again, wherein this would be a part of the first die, this would be a part of the second die. Next, we can have 5, 5, wherein we've got this as the first die, this as the second die. You can also try flipping this particular pair, but it will give you the exact same answer, which is 5, 5. So we are not doing that. Are there any other pairs which are actually giving us the answer 10 in a die? No. Right? Why is that? Because we have pairs like 8 and 2 which would give us 10, but they don't exist on a die. Right? We've only got numbers from 1 to 6 on a die. So these are the three pairs out of the sample set of 36 which is actually giving us a sum of 10. Therefore, the probability of this particular event, say it is E, will actually be equal to the number of incidences or the number of events where we're getting 10 as the sum divided by total number that is there as a part of our sample set, which would be equal to 1 upon 12. Again, a proper number. Right? So this was all on basic probability, wherein they're actually quickly gone through just what probability is. Next, let us look at conditional probability. Now, conditional probability is something which is slightly different. First of all things, it is more realistic in nature. What conditional probability does is actually it considers the probability that an event is going to occur when another event has already occurred. So here, the reason why conditional probability is more realistic is ideally because in conditional probability we are taking on more variables. We're not just considering two variables, we're considering, or one variable for that matter, we might be able to consider 3, 4 or more variables, and we are looking at how they work with simultaneously. Right? So if you look very closely here, you'll see that this is actually a variation on the multiplication rule. Our multiplication rule was that the probability of E and F occurring is actually equal to probability of E when F has already occurred into probability of F. If you just take this element to this side, or if I say this in a different manner, if I take this particular element to the other side, what I get is the conditional probability rule, wherein probability of E when F has already occurred is equal to probability of E intersection F upon probability of F. So this is the formula for conditional probability. So if, for example, here we've already picked an orange, then we can find out the probability of getting an apple by using this particular formula given here. right? So let us just quickly do this. Probability of getting an apple when we've already selected an orange is equal to probability of getting an apple and an orange divided by probability of getting an orange. The values are all given here, namely 4 upon 25 divided by 15 upon 25, which gives us a total of 4 upon 15. So this is the probability of this particular example here. Next, let us look at two very easily seen examples here. First is, if a coin is tossed 3 times, calculate the probability that you have seen at least one head if you've already seen at most one tail. So can you understand, they've given you at least one head and at most one tail. What is the meaning of at least one head? It means either one or two or even for that matter three heads, but we should already have seen at most one tail. At most one tail means that we've got zero tails or one tail, right? So let us look at our sample space. From our sample space, if we look at E, say this is event E and this is event F. The reason for that is because the probability that we need to find out would be event E and the probability of the event that has already occurred would be F, right? So if we take the probability of E, let's just give us a minute here. I would actually like it if all of you solve this together. Yes, so we've got our sample space as this. And here, probability of getting at least one head. So we identify the events first. Where are we getting at least one head? We're getting at least one head here, at least one head here, at least one head here, at least one head here. So in all of these events, we are getting at least one head, all except the last one. So our event E will actually have HHH, HHT, HTH, HTT, THH, THT, and TTH. So 7 of these actually come up as a part of E. Next, let us look at F. F is all of those instances where we've seen already at most one tail. So this means that we should already have seen one tail before getting a head. So because of that, we cannot consider this because as you can see, there are no tails that are seen before the head. Again, the second also can't be considered because after the tail, there are no other further heads. The third element here can be considered because after looking at a tail, we are then getting one head. Again, with this particular element, we can't consider it because after a tail, we're again getting a tail, not a head. Next, we can consider this element given here because after a tail, we are getting a head. Again, we can consider this element here because after a tail, we're getting at least one head. And similarly here, after a tail, we are getting at least one head. So as we can see here, F has a total number of 4 events within it or 4 entities within it. Now, probability of E becomes 7 upon 8 and probability of F becomes 4 upon 8, actually equal to 1 upon 2. So, what is the probability of getting E and F? Probability of getting E and F is actually finding out the common terms between these two. So, E and F both contain these terms. E and F both also contain this particular term. Again, these terms are contained within E and F. So we've got the probability of E and F as 4 upon 8. Again, so if we consider the probability of E occurring when F has already occurred, we would get this is equal to probability of E intersection F upon probability of F. Actually looking at this, you would find that we've got 4 upon 8 upon 4 upon 8, which is equal to 1. So this ends up being a sure event. If you are tossing coins in such a manner that you are tossing them 3 times, then the probability of you having seen one head after you have seen at most one tail becomes a sure event. It means it will happen, right? This is because both of the probabilities are dividing each other exactly and you're getting a probability of 1. Next, let us look at the second example given here. Now, as you've seen already, this whole situation of finding out all of these various values with a sample set becomes very heavy. So, what conditional probability does 90% of the time is that it asks you questions like these. Now, what are these questions, or what are these situations? These situations are ones wherein we are only asked to find out the probability of the intersection of two elements. Why is that? Because if we have the probability of intersection of two events, then obviously it becomes easy to find out the probability of one event occurring after another, right? So if you just look at this particular scenario, you can easily find out what is the probability of getting, say, 5 white toys, or 15 blue toys, or say for example 5 red toys, right? So the probability of picking out any one of these colored toys is very easily seen here. What is difficult? Actually finding out the probability of picking two toys in relation to one another. So let us see how that can be done here, right? So let us quickly analyze the question given here. We've got a question stating that there is a bag, and that particular bag has 25 toys in it. Let us consider a bag here with 25 toys. The toys are arranged in such a manner that we have 5 white toys, 15 blue toys, and we've got the remaining as red. So if you calculate this, you'll get that there are 5 red toys. Now we need to select toys in two ways. We need to select toys in such a manner that we are either picking out two red toys one after the other, or we're picking out a white one and then a blue toy. So let us understand this better with the buckets that I'm drawing here, right? So for each of these cases, I'll draw two independent buckets here, so that we're actually able to see exactly how this is occurring. So what I need to find out is the probability of getting a white and then getting a blue, and the probability of getting a red toy and then getting a red toy again. So can you see I'm constantly repeating the term and? That is because I am actually trying to find out the intersection, or I'm actually trying to implement the multiplication rule here, right? So how do we find this out? There is an easier, a more logical way to find this out rather than just blindly substituting our formula. So what we do is we actually analyze the question, draw a pictorial diagram of it, and then we understand exactly what is going on here. So if we have to pick out, say, a white colored element or a white colored toy from a bucket, we'll actually pick it from the set of whites here. So we are picking out one from the set of white. So the probability of picking out a white toy will be 5 upon 25. Right? Now please note here that this particular picking or selection is without replacement. What does it mean without replacement? It means once you've picked that toy out, you are not going to replace it. That means that the number of whites would become 4, and the total number of toys within the bag becomes 24. So the next time when I try to go and pick out a blue colored toy, what actually happens is that my probability becomes 15 upon 24. That is because now while picking out the blue toy, I only have 24 elements in my bag. Cancel out all of the common terms from here, and you will get the probability as 1 upon 8. So if you have the probability of white intersection blue, then it will become very easy to find out the probability of picking a white or the probability of picking a blue when a white toy has already been picked, right? So this is how we actually solve conditional probability questions. Let us take another example here. We've got red and red. So this means that we're picking out two red toys. So consider this red toy. When we pick out the first red toy, probability would be 5 upon 25. Then the number of red toys would decrease to 4 because obviously no replacement, and the total number of toys would turn out to be 24. Next, when we pick out the second red toy, the probability of getting a red toy would be 4 upon 24 now. Why is that? Because the total number of toys in the bag have reduced to 24. Divide, and you get your final probability of getting two red toys as 1 upon 30. Once you have the probability of getting a red and a red toy, it becomes very easy to find out the probability of getting a red toy once you've already picked out a red toy. So this is actually how we solve conditional probability. Let us look at one last last example for conditional probability, and that is on a deck, right? So what are we doing here? We are actually considering a complete deck of cards. I really like buckets, so I'm showing it as a bucket here. Now we already know that our deck of cards has 52 cards in it. We are supposed to actually pick out two cards, a first card and a second card. The first card has to be a red king and the second card has to be a black face card. That is what we have to find the probability of. What is the probability of finding out or picking out a red king as the first card and a black face card as a second card? Now, in order to understand this, again, we need to remind ourselves of what these types of cards are. So, if we look at red king, then there are two types of red king. One is a king of hearts and the other is a king, I should write one here because again there is one king of diamonds. On the other hand, if we look at black color face cards, now what are face cards? Face cards are all of those cards that have a face on them. So ideally king, queens and jack would be face card. Now if you're looking at a black face card, it means we've either got a king of spades or a queen of spades or a jack of spades, or we've got a queen of clubs, I'm sorry, a king of clubs, a queen of clubs, or a jack of clubs. So this means that in any deck we've got two red kings and we've got six black face cards, right? So if we are picking out the first item, let me just write that here as a part of my bucket. We've got two red kings and six black face card. And what we need to do is find out the probability of getting red king and black face card when we are actually trying to pick out two cards, and again this is without replacement. So what does the probability here become? When I try to pick out the first card, probability of me getting a red king is 2 upon 52, but after picking the card out, the number of red kings would become 1 and the total number of card in the deck would become 51. So next, when I go to pick out my black face cards, the probability here of picking those out would be 6 upon 51. Cancel out the common terms and we get something along these lines. So we've got 13 here. Yes, so this would be equal to 1 upon 13 into 17. So this is getting quite rare because there is a 1 upon 13 into 17 chance that this particular scenario would actually come up. So as you can see, once we've got this particular probability, finding out the probability of picking a black face card when a red king has already been selected becomes very easy now, right? So this is how we solve conditional probability. Now one thing to remember in conditional probability is the fact that conditional probability are actually based upon dependent elements. This means that if we've got any two elements, say for example, or any two events, say for example A and B, we are banking on the fact that these two are interacting with each other, that these two are intersecting with each other in some way or form within the environment. What happens if we've got independent events? Now, what are independent events? By definition, independent events are events that are not interacting with each other, right? So independent events are events that do not really affect each other. Why are they not really affecting each other? That is because they, even though they exist on the exact same environment, they might not be related to each other. So given here are two examples of this. If you've not gone to school today or maybe office today, then it will rain. Are these two events related to each other in any way? You not going to school or you not going to college or you not going to office, how does it matter, or how does it affect the environment in any way? How does it affect your weather patterns in any way? It does not. So maybe you've not gone to school and maybe it has rained on the exact same day, but there is no way in which these two would be related to one another. So such events that occur in the exact same environment but are not really related to one another are known as independent events. Now, in order to um, make independent events more accessible, what we've done is we have modified our addition and multiplication rules for independent events. Now, if you look at any independent event in a practical manner or in an experimental manner, you will find that the probability of E occurring when F has already occurred is actually equal to probability of E when E and F are independent of each other, right? So this means we are actually looking at both of these scenarios in their own places. That is because when looking at a Venn diagram, if this is our universe or sample space or environment for that matter, then E and F are actually formed like this. Can you see there is no intersection in between? So how does it matter whether F has occurred or not? It has no bias, or it has no relation to the occurrence of E. So the probability that E has occurred or E is going to occur when F has already occurred becomes completely dependent only upon the event itself, which is E. Right? Similarly, if we flip this, if we take the probability of F occurring when E has already occurred, again E and F are independent of each other, so it really does not matter here. The probability will actually completely be dependent upon by F itself. There is no component of E here in any case, right? So what happens to the addition rule? Very simple. Addition rule was probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. Is there any intersection between these two elements? No. So if we consider them as A and B, since there is no intersection between them, these disappear altogether. So what do we get as our addition rule? We get probability of A union B is actually equal to probability of A plus probability of B. So the sum of their individual probabilities. So the probability of A or B occurring is equal to the sum of their individual probabilities. Now if I add another C here, it's easy enough. Just add the probability of C at the end. Add another D, which is again an independent event. Add the probability of D at the end. And this can be extrapolated further for n number of events that are in the same environment but are independent of each other. Next, let's look at the multiplication rule. As per the multiplication rule, we know that probability of A intersection B is actually equal to probability of A when B has occurred into probability of B. Think about this for a manner, right? Look at this particular formula. P of E when F has already occurred is actually completely dependent upon E. So here, P of A when B has occurred will actually be equal to P of A into P of B. So what does this mean? The multiplication rule for independent events is such that the probability of A and B occurring is actually equal to the product of their individual probabilities. Right? Again, this can be extrapolated to multiple events. Say, for example, we've got intersection C. So here we can just multiply probability of C. Say for example, I'm sorry about that. Say for example, we have intersection of D. We can multiply another component here as probability of D, and so on and so forth. So because we've got a probability of events here wherein the events are not at all related to one another, this is how the multiplication and the addition rule are also modified in order to support independent events. The last thing you need to remember here before we go on to the sums very quickly is the fact that independent events here are of such a type that if two events, say for example A and B, are independent of each other, then even their negations or complements will be independent of each other. This means that if we take A dash and B, both of these will also be independent of each other, just because A and B are independent of each other. Again, if you take A with B dash, we would again find the same thing, that these two are independent of each other. Lastly, if you take A dash and B dash, again these two would be independent of each other. So if you take any variations of the sets that are actually independent of each other, then their complements would also be set which would be independent of each other. So complement of one of the events under consideration or complement of all of the events under consideration. If you take their complements and they were originally independent of each other, then the complements of that event will also be independent of each other. Now, just a quick review: complement of an element or complement of an event is actually the possibility of an event not occurring. So if we've got P of A such that this is the probability of A occurring, then P of A dash will be the probability that this particular event will not occur, and that would be equal to 1 minus probability of the event actually occurring. This is an important formula and it is often used. Another important formula which is often used is that probability of A union B is equal to probability of A intersection B. Similarly, if we take probability of A intersection B, oh, I'm so sorry here, I'll just quickly change this. There was some error here. Yes. So this is actually supposed to be B union A. So as you can see, probabilities or here union and intersection are commutative. It does not matter what order you use to actually define or write down the set. Till it is union, it will always be the same value. So A union B's probability is equal to B union A's probability. And similarly, A intersection B's probability will be equal to B intersection A's probability. Right, so let's quickly jump on to our last set here, which is sums. Find the probability of getting 1 on a dice and a head on the coins. Independent events, right? Rolling a dice, rolling a coin, two completely independent events. So let us call this A and let us call this B. What is the probability of A? Probability of getting 1 on a dice is 1 upon 6. Probability of B, which is getting a head on a fair coin. Now please note, we are considering that both the dice and the coin is both fair. So probability of getting a heads on a coin would be 1 upon 2. So what is the probability of getting a 1 on the dice and getting a head on the coin? That would be 1 upon 6 into 1 upon 2, which is equal to 1 upon 12. So as you can see, we've used the multiplication rule for independent events here directly, and that is because of this and here. So this and told us that it is intersection that is required. So we use the multiplication rule. And how did we use it? Multiplication rule states that for independent events, probability of two events occurring together is equal to the probability of the independent events. Right? Next, let us look at the second question given here. Yes, so what is the second question given here? There is a random student A, there is a random student B. There is a probability that these two students will complete their homework. What is the probability of only one of them completing their homework? So what is the meaning of one of them completing their homework? It means that if A has completed the homework, then B has not completed their homework. Or say for example, B has completed the homework, then A has not completed their homework. That is what this means, right? That there is a we need to find out the probability of only one of them completing their homework on any given day. So how do we actually match this up, or how do we convert this into probability? We actually look at this whole thing. So we said we need to find out the probability of A completing their homework and B not completing their homework, or the probability that B has completed their homework and on the same day A has not completed their homework. So this is how we can find out the probability. Now we know for a fact that till these two people are not copying, and we are assuming here that these two people are not copying their homework from each other, then we can say that these two people or these two students' homework completion is completely independent of each other. Right, so if it is independent of each other, then probability can actually be found out using the multiplication rule. So we'll have probability of A into probability of B dash plus probability of B into probability of A dash. Now probability of A is very clearly given here as 2 upon 5 and probability of B is very clearly given here as 4 upon 7. How do we find the probability of B dash? Very simple. We take the probability of B, subtract it from 1, and we'll get the probability of B dash. So 1 minus 4 upon 7 would give us 3 upon 7. So we've got probability of B dash as 3 upon 7. For carrying out a similar calculation with probability of not A, we would get the probability of not A as 3 upon 5. Calculating this, we would get 6 plus 12 upon 35, which is equal to 18 upon 35. So the probability that only one student has completed their homework between student A and B is 18 upon 35. The last question we have here on independent events is to find out the probability of a die rolling to a 6 if it is Monday or Tuesday. How does it matter if it is a Monday or a Tuesday? What relation does it have to the die rolling a 6? None. So the two events given here are independent of each other. Let this event be D, let this event be empty. Alright, so the probability of getting a D, that is the probability of rolling a dice and actually getting a 6, is 1 upon 6. On the other hand, the probability of getting a Monday or a Tuesday is actually equal to 1 upon 7 plus 1 upon 7. Now, why have we done this? Because Monday and Tuesday are not really that related to each other, and we just want to find out whether Monday or Tuesday is coming up on that particular day. So, we have a sample set in a week of 7 days, and we've selected Monday. So, the probability of giving a Monday would be 1 upon 7, and the probability of getting a Tuesday would again be 1 upon 7. So, the total probability of getting either a Monday or a Tuesday would be 1 upon 7 plus 1 upon 7, which is 2 upon 7. Next, we need to find out the total probability of getting a dice to roll to 6 and to get a Monday or Tuesday. Right? So, how do we find out the probability here? Probability of getting a dice to roll a 6 into probability of getting a Monday or a Tuesday, which would be equal to 1 upon 6 into 2 upon 7, which would give us 1 upon 21, which is again a proper fraction. So, this is how independent events are carried out. So, in this whole session, now this is the end of the session, right? In this whole session, what we found out is that we have probability and we can use probabilities to solve various real life examples, and any and all conditions in probability can actually be extrapolated further to find out how it would fit a particular given situation. So what we've seen here is what is probability, right? We've also seen the applications of probability. We've seen the real life applications. We've seen the computer science applications. Next, we've looked at what basic probability is. We've looked at what the addition and the multiplication rule were. And we also found out, or we also carried out some sums based upon this multiplication and addition rule. Next, we looked at, I'll just repeat this quickly, conditional statements or conditional events or conditional probability, which was actually the probability of dependent events. So we saw how dependent events would interact with each other in any given scenario, and how we could solve some problems wherein two events are dependent upon each other. Lastly, we looked at independent events, and we saw how conditional probability reacted for these independent events, and because of that, how did the addition and multiplication rule change for these particular events, right? So we had a look at all of these, and we also practically implemented all of these in the form of some sums, right? So that brings us to the end of our session on probability here. Again, if anyone has any doubts, any queries, or any further requirements from this probability series, please do put it on the chat section so that they can be addressed and that we can take up all of those queries in the further session. Now I'm going to stop for a certain amount of time, namely 5 minutes, and let us see if anyone has any questions. So, for those of you who do not have any questions, thank you so much for attending this session. And the others can please put up all of their questions on the chat given here, or if you have some other requirements from me regarding further complicated topics in probability or some such, please put those on the chat too. Thank you so much. Okay, so a quick scrub of this. Yes. So there are no questions as such yet. When will I upload the next video? The next video will be as per the schedule. You will get a notification for the same whenever that video might be. Please make a note of that notification and please do attend it. Okay, as you like it, one of the best ways to retain the knowledge that you have gained today is, first of all things, note all of this down. Second of all things, practice. With computer science, with any kind of programming, with any kind of discrete mathematics that you're studying, with any kind of machine learning concepts or data science concepts that you're doing, one important thing that you need to remember is that you need to practice those concepts. Any logical or conceptual concept cannot be retained till you don't practice them, till you don't implement them regularly. So treat data science like you did maths in your lower classes. Sit, retain the knowledge, practice it. There are n number of resources on Great Learning. There are n number of worksheets that are there online, which you can actually go through and you can actually understand, right? So please sit and practice the questions. What you could also do is you could go back, pause the video. This particular video will be uploaded onto the Great Learning page, YouTube page. So what I would recommend you do is actually you can go back, you can watch the videos and you can solve the questions by pausing the video at regular intervals whenever there are questions. That would actually help you in practicing, right? Another thing you can do is each and every concept that you have, if you have any doubts later on while you're practicing, you can actually put down your doubts also in the comment section here so that we can answer them. All right. So please make sure that you're actually doing that. Abhishek Kumar, I've actually not understood your question here. If you could please just elaborate on it because there are just two words given here on this. Okay. So if there are no more questions from anyone, again, I would actually advise you all to put down your questions here. All right. So if there are no more questions from anyone, let's take our leave and this would be the end of the session. Thank you so much for to all of you for attending this particular session. Stay safe, social distance and make sure you're healthy